In this video, I would like to walk you through the steps that you need to take if you want to analyze your data in terms of brain connectivity between the generators of oscillatory activity. This diagram shows the steps that you need to take. After loading your raw data, you select the montage or source montage of interest as a first step. You then define your paradigm and define the conditions of interest which you want to analyze in depth. When you then launch BESA Connectivity, the data will automatically be exported, and the time-frequency workflow in BESA Connectivity will automatically be started. After walking through the transformation of the data into the time-frequency domain, you then start the connectivity workflow, which will crunch the numbers and present you with the connectivity between the montage channels of interest. Now let's see how that works in the real world. Here I have my data, which is a resting state recording where some auditory oscillatory activation was superimposed as a simulation. Let us first of all transform this data into source space using a user-defined source montage. This 9-channel montage has 4 auditory sources that cover our simulated activity and 5 additional sources that model non-stimulus related background brain activity. You can see the stimulus events at the bottom. Trigger code 1 denotes the onset of an evoked auditory activation, which is followed by the simulated oscillatory activity at varying intervals. The activity was simulated with a low signal-to-noise ratio and is thus not apparent in the non-averaged data. Now, as a second step, I'm going to define the paradigm for this experiment. I press the ERP button and open the predefined paradigm file for this experiment. This gives me 2 conditions. I'm interested in the first one, which marks the evoked activity. Check the epoch that I will look at. It is set from -400 milliseconds to 1200 milliseconds after the stimulus. Let us run an artifact scan to discard epochs which carry artifacts. We will keep 82% of the epochs, which is shown here at the right. Now go to the Coherence tab. I'm going to start my condition of interest here, which is the ST on condition. Then I simply press the Start Connectivity button. This now exports the epoch data to a simple binary format and then starts BESA Connectivity. Let me bring up the icon and press the Accept button. I can see that I am already in the time-frequency analysis workflow, as is shown here on the left. Now I need to decide which method or methods I want to use. I will go for complex demodulation as well as wavelet transformation using Morley wavelets. The next step is to load the data. The data are already pre-selected as the one I just exported from BESA Research. I can see a summary of the data here. The next step gives me a trial-by-trial overview in this top viewer. I could now discard trials, but I'm not going to since I already discarded the artifact trials in BESA Research. I can also adjust the parameters of the time-frequency methods, but I will stick with the default parameters for now. I will just change the maximum frequency to 50 Hz since we are not interested in high-frequency activity in this experiment. Then, in the next step, I will run the time-frequency analysis. This brings up the temporal spectral evolution of the data in the 9 source channels that I have in my source montage. The source montage disentangles the brain generators very well. We can see 2 peaks for the evoked activity and 2 for the oscillatory activity. We can finish the workflow now and save the project. I would recommend to put different experiments into different groups and to include the montage name into the file name. So here I will call it ACOSC5 SRC RC1 CD Morlaix. Then I have the original file name, montage, and method names covered. The final step is to perform the connectivity analysis. For this purpose, I will start a connectivity workflow. The first thing to decide is which connectivity methods I want to apply. I will try coherence, imaginary part of coherency, and Granger Causality. Then I need to load the project. Luckily, the time frequency project I just finished is already pre-selected. Now I see the time frequency result again. I can now adjust some settings from the Granger Causality analysis, but I will just stick with the defaults and start the connectivity computation. Now the program goes through the different methods for connectivity and repeats this for each time frequency method too. That will take some time to compute, but since we have an optimization for multi-core processing, it finishes the job quite quickly. After it finishes, we can see a matrix plot of all channel-by-channel connectivities, showing first of all the coherence plot, since this was the first method that I selected. Let me first switch to the Morlaix wavelets and then select the channel pair with the most significant coherence outside the alpha band, which is between the two auditory channels where the oscillatory activity was simulated. I can click onto the highest activity now and switch to 3D mode to see the connectivities in 3D. Let me switch to imaginary part of coherency. Just change the scaling slightly to bring up the connection arrows. Now you can see that the right auditory area drives the left, something that was not evident from the coherence plot. How about Granger Causality? This signal is somewhat weaker, but I can go back to the matrix plot to scale it up a little. Then back to the 3D. And I can just see that the Granger Causality gives me a similar result to the imaginary part of coherency. In the next video, you can learn more about the different settings and options for connectivity analysis in BESA, and also how to create publication images and videos from the results.